Thank you for inviting me. I'm Venkatram Vishwanath from the Argonne National Laboratory. I lead the data sciences group at the Argonne Leadership Computing Facility, and I'm thankful for the invitation and glad I could talk to you about some of the data science that we are doing currently on our big systems, as well, give you some insights about where we are going towards at Exascale and the data science applications that we foresee on our big systems. And at the end, I'll also talk about some of the data management aspects, the networking aspects that I believe this community would be very much interested in. A lot of these slides, I've got contributions from folks such as at Argonne, Nicolas Ferrier, Ian Foster, whom you may know, Bobby Kasturi, who's a scientist, Mike Papka, Catherine Riley, and Rick Stevens as well. And I would say that a lot of the work that's being done is by folks in my group who do a tremendous amount of innovative work. The group consists of computer scientists, computational scientists, applied mathematicians, software developers, and they work on really innovative and grand challenge problems. And we do this working very closely with science. So I would say that they're responsible for all the cool work that goes on. So I wanted to give a brief introduction to the Argonne Leadership Computing Facility. We are a Department of Energy Office of Science user facility, and we operate some of the largest supercomputing systems for the Department of Energy, and this is focused on open science research. And we have two production systems right now. One is Theta, which is an Intel Cray system, and we have Mira, which is an IBM Blue Gene Q system. And the mission of ALCF is to take our expertise in data simulations and learning and work with applications to get production science on our big leadership facilities. Our users span academia, that is universities, national labs, other agencies, as well as industry. And the users are both located in the US as well as in the rest of the world. So the focus of our facility is all about open science research. And I'll talk about some of the allocation programs we have. So just to give you a historical perspective, we started in 2007 with the Intrepid Blue Gene P system. From there, we went to Mira, which is the Blue Gene Q system. We have Theta, which is IBM Knights Landing-based system. And in 2021, we'll have Aurora, which will be one of the first exascale systems in the US. I'll talk some more about it. So there are many different ways to get projects and accounts and access to our system. The main workhorse to get access to our system is the DOE Insight program. This is administered by Argonne Leadership Facility as well as Oak Ridge, which is our sister lab. And around 50% of our time is allocated to the Insight projects. So Insight is a peer-reviewed competitive proposal where you have to talk about a compelling science case as well as a computational readiness to run on large-scale supercomputers. Again, this is open science, so folks in academia and universities should also apply, and they are one of our biggest users. In this calendar year, we'll give around 205 million node hours. That translates close to 2 billion core hours for Insight. In addition to Insight, we have 3 other programs. We have the Oscar Leadership Computing Challenge. This is administered by Department of Energy. This is more for high-risk, high-reward programs. We have around 20% of our system allocation reserved for the DOE Exascale computing project. So this is more looking towards the future. And we have around 10% of our allocations for more discretionary allocations. So if you want to get started on our system, learn how the infrastructure works, how to scale up, the goal is to apply for an insight or an ALCC based on this allocation. So traditional HPC systems have been very much focused on large-scale numerical simulations. And where we are moving towards is using large-scale supercomputers to do simulations, scalable data analytics, as well as deep learning. And this is one of the key focus for the Coral class of supercomputers. So Coral is the collaboration of Oak Ridge, Argonne, and Lawrence Livermore Lab. And where the goal is to jointly procure large-scale leadership supercomputers for Department of Energy. So as you know, the number one system right now is Summit, which is at Oak Ridge, is part of the Coral procurement. And in 2021, we'll have Aurora, which will be the world's first, the US's first exascale system. And this is a collaboration between Intel and Cray, as well as Argonne. And the goal of this is threefold. One is to really support large-scale simulations. It will have features that enable data-intensive applications. And I'll talk some more about them. You can think about it as ways by which you can have big fat pipes coming in, as well as stacks that will enable data-intensive computing. And it will have capabilities to enable deep learning and various AI at scale on these large-scale supercomputers. So let's look at what are these classes of applications that we expect on these exascale systems. And I want to point out that a goal for us is not just flops, it's performance for applications. So the target for us is achieving 50x signs over the existing 20 petaflop system. That's how we measure our metrics. So if you look at these simulation applications on the left, now you have your traditional simulations in cosmology, material science, combustion, but you also have some new simulations that are coming up. You have the quantum simulations that are there. You have transportation networks as well as brain simulations that are we've been having some good success in. In addition to that, one of the key focus areas for our exascale systems are big data applications, such as the workloads and analysis that we need to do for APS, high energy physics, the LSST and SKA, and how to enable analysis of these large-scale workflows and as well as the data sets is a big target for us. And then finally, on the right column, you see all the deep learning applications. We have a few good success stories in this, and we are seeing it being adopted in science, in health, healthcare, material science, combustion, across a wide variety of scientific computing domains. So let's think about, from a hardware architecture perspective, what are the key things that we need? From a simulation perspective, we need very high compute intensity. We need very high memory bandwidth. So you're looking at systems such as high bandwidth memory and future generations of them. You need really high memory capacity. So in our procurements, if you look at the latest Coral 2, we are targeting around 6 to 8 petabytes of memory on these supercomputers. We need large coherency domains. This is something that simulations need because they want big data set sizes. A unified address space between both the CPU and accelerators, if you have accelerators on your systems. For big supercomputers, we look at the bisection bandwidth, and this is usually in the petabytes per second range in our machines. That's a range that we're looking at. Injection bandwidth, that's the amount of data that a single node can push out. in our supercomputers, we're looking at in the hundreds of gigabytes per second. And you won't have a supercomputer if you don't have a very low latency communication interconnects. And the target I/O bandwidth that we're looking at is in the range of tens of terabytes per second here. So that's simulation. Now, if you look at our data application, they have requirements that are very similar to what the simulations have. And in addition to that, they need big fat pipes that can come into our big supercomputers. We're also seeing a need for a very flexible software stack, ability to run, say, containers, the big data stack. So our current supercomputers are able to run containers such as Singularity, Spark at scale. We are looking at workflow support. So you have several scientific workflows such as Pegasus, we have BALSAM, Swift. These are areas that we need to support. Scripting languages are becoming very common in big data applications. And we also need to have very flexible scheduling policies to account for interactive and different new workloads that we are seeing. So finally, if you look at learning, some of the key requirements here are support for 16-bit, 32-bit, reduce precision. Again, you need to have large coherency domains, large memory bandwidths. We're seeing larger and larger models that are being designed and developed in deep learning applications. So one of the key goals is to have fatter nodes there. And another very critical aspect is the data sets that we are seeing are very sparse in many cases. So very effective hardware support for scatter and gather operations are very key in this case. So this gives a very broad overview of what kind of architectural features are we looking at in these systems. So thinking about this, in 2015, we started a program at Argonne called the ALCF Data Science Program. And the goal was to really think about how do we enable data-intensive applications as well as simulations and combine them together to get real science done on big supercomputers. And these span either both computational science, experimental, observation sciences. And the focus was to look at enabling either advanced statistics, UQ, image processing, machine learning, deep learning on our big supercomputers. These are 2-year proposals. It's right now in the 3rd year. So every year we grant around 4 funded projects. They get time on our big supercomputers, as well as they get funded in part by postdocs, and they get support from our data science staff as well. And this is a really exciting project because we've got several novel, innovative science that have come out from this. And this gives us an idea about where should we be taking our current programs such as Insight, and how should we support simulation, data, and learning for our open science application. So I'll quickly walk through 2 or 3 applications that are part of the ADSP program and that I'm closely involved in. The first one is on design of dye-sensitized cells. So imagine a window which has a coat of a dye, and that can act as a solar power cell. That is the goal of this project, designing these dyes. And the reason we want to design these cells is that around 40% of the energy usage in the US comes from buildings. So if you can make these buildings more energy efficient, we can be more energy independent. And one challenge with some of the solar cells that we get is that they're manufactured with rare metals and minerals. So it's very expensive to manufacture them. And the efficiency is also low. So the goal is how do we fabricate and come up with solutions that are easy to manufacture and have the properties of interest for us. So to tackle this problem, we took a very different route. And the PI of this project is Jackie Cole, who's she's the head of the molecular engineering at University of Cambridge, and she has a joint appointment at Argonne National Laboratory. And the approach that we took was, there's a lot of existing materials that are captured in publications. So we wanted to mine them to see what are some materials of interest. So in this case, we have a text mining tool that has gone and mined close to 300,000 publications. Actually, as of today, we are at 800,000 publications that we have mined. This looks at both text as well as figures to see materials that have been published, what kind of properties they have, and it's very focused on chemistry data sets and material data sets here. So we first have a text mining and figure mining tool that we go and extract data from our publications. We feed them into a database over here. And in some cases, you have a lot of incomplete data sets. So we use various machine learning techniques to either it's a regression problem where we fill in these blanks, or we use either time-derived density functional theory or simulations to generate the properties of interest. So from these enriched data sets, we are now looking at our target materials of interest. So we're looking at techniques, again, using deep learning, such as graph convolution networks to get structures of interest over here. And finally, once you have these materials of interest, we've actually fabricated them and to validate their properties. And so we have some very exciting results that is currently in review. The entire project has already been, we have published work at the American Chemical Society, and we have existing some exciting work in review right now. So the second project that I'm going to talk about is trying to reconstruct the connectivity in the brain using electron microscopy images. So this is the work that, again, it's funded by part of the ADSP project. Bobby Kasturi and Doa Gorsai are the PIs of this. In this case, you take your specimen that you want to image, and you use electron microscopy to get really thin slices of images. So we have an EM facility at Argonne National Laboratory where we image this. So each of the images over here are 60,000 pixels by 40,000 pixels. And we have around 1,000 to 2,000 of these, depending upon the experiment that you do. Let's see if this plays. So this gives you an example of what we are trying to understand. We take these images and we are trying to reconstruct the connectivity. So in this case, you're looking at some of the axons. You have the dendrites in the red over here. You have some of the glias that are there. And we want to identify which are some of the inhibitor axons, and this helps us understand plasticity. So the overall goal is to really understand the connectivity of the brain here. And the data sets that we are looking at are the mouse brains here, and the sizes are in the terabytes. And if you go into the more fine-grained data sets that we get, it's around 4 petabytes in size. So this is the size of a mouse brain. And where we want to go is to look at right here, which is the human brain. And this is at least an order of magnitude larger than the current experiments that we have ongoing. And This is one of the really large compute-intensive deep learning projects. So after we get the images to do the reconstruction, we use deep learning in this case. We have models that are based on 3D units. We have another that's based on flood-fill networks. The flood-fill networks that we have used have run at scales of 2,000 nodes of our entire supercomputer, which is half our supercomputer. And a training problem typically takes us close to 12 to 16 hours on our big machines here. And these are for really tiny problems of training. So in addition to this, we are seeing a number of other very interesting data and learning projects. The one on the left over here is work that we have ongoing with GE Research, where they're trying to build better turbo machineries and turbines. In this case, they're trying to do several reduced order models. We have a project with LSST workflows on our system. Right here at the bottom is a project that's led by Alexander Tarchenko, who's at University of Luxembourg, who works with folks at Cornell as well as University of Washington, where they're trying to understand crystal structures and prediction of many-body interactions. And on the very bottom left is work that is taking place in hyperparameter optimizations. As you heard on the very first day, folks at Google talked about hyperparameter optimizations being one of the big challenges in deep learning. And in this case, we have several model-based search approaches that have scaled out to our big supercomputer as well. So we have approaches including GA, random search, grid search, and model-based searches as well. The final project that I'll talk about is the Candle project. Candle is led by Rick Stevens. It's one of our flagship Exascale projects that we have for deep learning. And it tries to solve 3 pilots that scale from design of drugs, what's the response of drugs given a patient's genes, as well as looking at how to plan for treatment strategies for a population. And again, this is one of the projects that has scaled on our big supercomputers at our end. So in DOE, we are seeing a wide variety of applications spanning multiple different science domains over here. So to prepare for Aurora, we have funded 10 projects. And these 10 projects would be one of the first to scale their data and learning problems on the Exascale machines. And as you can see, these projects span a wide variety of science. We have university PIs, we have national lab PIs over here. And in some cases, for this community, this talks about the various projects that we have here on the left and the different kinds of methods that they capture or they will be exploiting on our big supercomputer. I'll just go to the other view and I'll try and highlight, maybe something that this community would be interested in, which is advanced workflows. Advanced workflows also includes streaming of data from remote sites. And as you can see, we have pretty much most of our 10 applications who are interested in high-speed networking here. So that was Coral, and we already have Coral 2 that's out. Coral 2 is is planning for our supercomputer that comes beyond Aurora, and we are currently in the procurement and the acquisition phase right now. The proposals from the various vendors were due in May, and we are under the review process. Over here is a link to the benchmarks, and our group at Argonne and ALCF, we were responsible for the deep learning benchmarks to help with this procurement. So I'm going to shift the conversation more to data management and networking. So we use Globus to manage and move data from our supercomputing center to our users. So Steve Tiki is in the audience, and Globus is what we use for pretty much most of our production data movement in and out of our facility. And what's really impressive about Globus is that it's got 12,000 active endpoints. That's phenomenal what Globus has. And Steve is around, and I would say that you should reach out to Steve for any questions that you may have. So we've been preparing for managing vast streams of data that we get from facilities at Argonne, as well as from our users. So here's a chart that talks about the data volumes being generated by the advanced photon source, which is at Argonne. So currently, today, it produces around 165 terabytes per day. That's the volume that it generates. And with the upgrade that's coming up for APS, it's going to increase by a factor of 10. So we expect this to be at 2 petabytes per day. That will be the amount of data that will be generated by the APS system. So one challenge that we face is, yes, you have these large volumes of data, but the end users, institutions, may not have enough storage to take in these streams. So we have a pilot project at Argonne where ALCF is working closely with the Globus group on a system called Petrel. So in Petrel, you could stream your data from all the instruments as well as from our facility to this storage system. I can give you details of it. But the goal of this system is that once you have the data products, you want to share it with your collaborators. You want to publish it to your community. And your community can come to our systems and they can access the data sets. They can run analysis against these data sets. So we have Kubernetes that enables us to do that. And you can also stream data out from here, from these nodes out to the wide area network. So we have 100 gig connectivity to ESNet, and from there we could go out. So the main goal of this is to make data sharing and collaborations really easy. And as a project PI, you have complete control on whom you can share your data with. You can create accounts for them using Globus Auth, and you can make this either accessible to your collaborators, or you can make it accessible to the wide public as well. So this is the goal of this project, is to make it easier to share data that you get from facilities and instruments to the community. So as of today, we've stored around 1.4 petabytes of data. We've transferred 22.2, and we have close to 320 users, and this is from 2017. And our users and usage of the system has really increased. So in the interest of time, I'm going to skip on this, but in short, a big challenge that we have on facilities is production workflows that just work. And at Argonne, we have designed BALSAM, which can coordinate workflows between multiple different sites. The Atlas Computing has used this to run on our systems. As you can see, here is the Atlas Computing running on 48,000 nodes, 768,000 cores, using BALSAM as the workflow manager. We've used it with some of our real-time fusion experiments, and we've delivered close to 150 million core hours of production science using this. So I'll finally close with a project that is gaining a lot of momentum at Argonne. This is the Waggle project, where we worked to build sensors, such as right here, which can try and understand how much of what's the air quality, how much carbon monoxide is there. And then we can put it in these platforms, such as right here. And these are Waggle boxes. So think about them as sensors that you can deploy all over. We have 300 of these sensors, Waggle boxes, in the city of Chicago. And many of these boxes are being placed in areas which are of, where we don't have enough data or are economically challenged. And this way we can actually get a lot of additional information from these places on what's the air quality, or how should we be improving deployment of our city services in Chicago. Intel is actually taking this and productizing it. The software platform is really open, so you can go to Waggle or wa8.gl. You can get information about the hardware. You can replicate this. You can get information of the software. It's open source, so you can even use this for deployment. And we've actually used this in several cases. What you see on the left is for tracking pedestrians. So there's a video. This video was basically generated from one of our colleagues in EU. And we can use these Waggle boxes to track pedestrians. And here at the very right is the Waggle boxes that we have on Lakeshore Drive in Chicago. This way we can understand if there's some flooding, if there are some snow that needs to be removed, and it can help with our planning of the city services as well. So with that, I thank you for your attention and happy to take any questions you may have. Thank you.
Right.
That's
How
right.
is that compared to doing training on GPUs?
Yeah, so it really depends on what kind of a GPU you use. I would say that from what we've seen in terms of performance, for every 2 Xeon Phi nodes, you get the performance of a single GPU. And what you have here is a large scale of Xeon Phi, so you get very power efficient, scalable learning as well. Yes.
So I wasn't paying enough attention to you lately. So is the machine that Aurora will be now public?
No, it's not public yet.
Okay.
I liked the description of Petrol. And Petrol looks like a really nice back end for some of the data portal stuff that I was actually mentioning earlier. Do you know if people are doing that sort of thing with Petrol at this point, or are there plans to do that?
So we have several data portals that exist right now on Petrol. We have one that deals with cosmology. There's another that is on the materials data facility. We have one with the Ramses as well that I believe you're part of. So we have multiple data portals over there and we have APIs that facilitate building portals on this infrastructure.
Fantastic, thank you.
All right, thanks again, Venkat.
Thank you.